Vijay. He's a staff research scientist in brain team at Google Research US. His research focuses on building safe, reliable, and trustworthy AI, including concerns like privacy, uncertainty estimation, fairness, and formal verifiability. Title of his talk is Reliable AI via Formal Verification and Human AI Collaboration. I'll give you soft signal at 5 minutes. Sounds good.
Am I audible in the back? Yeah. Okay, great. Thanks again to the organizers for putting together this event and for inviting me. It's a pleasure to be here. So I'm going to talk about how to build reliable AI systems by thinking about how humans and AI systems can work together. So just to set the stage a little bit, so I was just thinking, like when I was a student in India, like back in 2008, events like this didn't happen, and machine learning was still a specialized field within computer science. It wasn't as pervasive as it is today. And we've seen incredible progress, at least in the last 5 years or so. So it doesn't seem to be working. The clicker doesn't seem to be working. Oh, sorry. Okay. And so we've managed to train AI systems to play complex games like Go better than the best humans in the world. We've managed to train AI systems to fold proteins, to generate art and images that are appealing to us, and to do a lot more with the latest favorite toy of everyone, ChatGPT. So this is all incredible progress, but the question is, does this mean that we should all just go home and the problem is solved? Not quite. So despite ChatGPT having all these amazing capabilities, you can get it to do silly things like prove that the square root of 4 is irrational, and it'll give you a proof that seems quite convincing, except for like one step in the proof being incorrect. Or like there's this recent paper that shows that by training adversarial policies to, you can essentially bring down the success rate of some of the state-of-the-art Go AI-based Go players in the world, and essentially fool them into like essentially giving away the game, right? So this shows that like even though we have these powerful AI systems, we are far from making them fully reliable and robust. So the focus of this talk is going to be to try to see whether by leveraging human AI collaboration, can we improve the reliability of AI systems? And what are the technical challenges associated with this? And what are the research directions that I think are interesting going forward? So if we think about human AI collaboration, there's a whole hierarchy of possibilities. So the first is what I call complementarity. And the idea here is that we have AI systems that know when they are not able to make a reliable prediction. And in those cases, they can defer to a human expert, right? The next level above this is a cooperative AI system where it knows when it cannot make a reliable prediction, but then it also knows that it can ask for additional information and it can ask for specific pieces of information so that it is able to make a reliable prediction. And the final is, fully interactive AI systems where you can imagine having a natural conversation or some kind of exchange of information between an AI system and a human decision maker. And at the end, the goal is to produce the best possible prediction or decision. So I'm going to talk about primarily the first two boxes here and outline some research directions, which I think will be important to try to solve the third. So the first project I'm going to talk about is something that we did to try to see if we can take some of the medical AI systems built at Google and elsewhere, and layer this notion of selective deferral on top of that to make them more reliable. So this was a big collaboration involving the health team at Google, DeepMind, and some external partners. Okay. So there's this paper published by folks at DeepMind and Google a couple of years ago, where they trained AI systems to diagnose breast cancer from mammograms. And they noticed in the evaluation of this paper that both AI systems and expert radiologists tend to make mistakes in this type of diagnosis, but the mistakes that they make are not exactly the same, right? So there is some essentially the cases that the AI system gets wrong are slightly different from the cases that the humans get wrong. And this already suggests the possibility that if you could figure out which cases are better diagnosed by which, you can actually have a more accurate system, right? So the main technical problem we're trying to solve is that we receive as input a medical image, and our goal is to decide whether we want a human clinician to diagnose the image, or we want to ask an AI system to diagnose, right? So the goal would be to see if can we build what I'm going to call a deferral AI, which will predict whether the medical case is more accurately classified by an AI model or by a clinician. So in terms of how the systems looks at deployment time, the idea would be that you first take the medical image, you pass it through the AI system, you get the predictions and the associated confidence scores, and then you ask the deferral AI system, like, is it okay to rely on the medical AI system to make a prediction for this case? If not, you would defer to either one or more clinicians, and that's the overall system in terms of arriving at a final decision for whether the disease is present or not. How do you train these kinds of models? So we're going to take a data set consisting of a bunch of medical images, and we're going to get the predictions from the AI system and the associated confidence scores. And we're also going to ask a bunch of clinicians to diagnose the same. And then we have this big data set, which is the medical images, the predictions of the AI system, and the clinical opinions. And based on this, we're going to try to learn the deferral model. One more thing I forgot to mention is that, like, we also assume that we have a ground truth label for these cases. So in the data sets that we're working with, it comes from a screening program where all the participants go through like a biopsy in case they're judged to be at risk of cancer. And so we have the ground truth labels as well. Okay, so our focus on this work was to look at this black box deferral setting. So the idea is that the deferral AI doesn't have any access to the internals of the diagnostic AI models, right? So the pointer doesn't seem to be working, but what's in the green box, which is the medical AI system that's trying to make predictions, is pretty much a black box as far as the yellow box is concerned, right? And our motivation for doing this was that we didn't want to, okay, so I'll discuss the motivation on the next slide. But if you have such a system, then what you can end up learning is something quite simple. So we have on the x-axis the confidence score of the AI model. 0 indicates that the model is very confident the disease is absent, and 1 indicates the model is very confident the disease is present, and intermediate scores indicate uncertainty. And so the idea is that, like, when the model is very confident or of either the disease being present or absent, you would prefer to use the model. And only in the cases where the model is not very confident, you would defer to a human expert, right? So the main goal here is to learn this kind of regions of confidence scores where the model is less likely to be accurate relative to a human expert. So advantages of black box deferral is that, you know, you can apply this to models that come from third-party vendors, even if they have IP restrictions that don't allow you to access the internals of the models. Because this is a medical space, there may be regulatory restrictions that prevent you from changing any of the internals of the models, even if you have access to them. And finally, like we wanted something that's very simple to implement and recalibrate if you have some distribution shifts. So if you train it on one population of patients, but you want to generalize it to a new population, you want to be able to do so with a very limited amount of data. So if all I'm doing is to learn thresholds, then you might expect this is a very simple machine learning problem. But the challenge is that you need to do this with very sparse data as well. So what I'm showing here is one of the data sets that we worked on. And each data point is represented by, if it's represented by an upwards arrow, it means that it's a data point for which the human made the correct prediction, but the model did not. If it's a downward arrow, it means that the model made the correct prediction, but the human did not. And the blue and the black mean that either both were correct or both were wrong, right? So the interesting cases as far as deferral is concerned are where you have upwards arrows or downwards arrows. So we want to defer in regions which cover all of the upward arrows and exclude all of the downward arrows. So if that's our goal, you could imagine picking these two thresholds as the thresholds between which you defer, or these two thresholds, or these two thresholds. So all of these will give you exactly the same performance on this data set, right? Is that clear to everyone? Because essentially, like, the only thing that affects performance is being able to defer when the model would be incorrect and the human is correct, right? So the question is, like, how do we choose between these multiple solutions? And the idea was to adopt a probabilistic approach, which allows us to do some kind of smoothing. And the end result of that probabilistic approach is that we get a smooth estimate of what we call the advantage function, right? So the advantage function tells you, like, whether a human is more likely to be accurate than the model. And based on the advantage function, you can decide whether it's better to defer or to use the AI system. Cool. So how do we estimate this advantage function? The key insight is that we just need to estimate a bunch of probability distributions. So we're going to look at the joint probability of the confidence score of the AI model and the clinician prediction given the ground truth label. And we're going to assume that the ground truth label is a binary label, as well as the clinician prediction also is a binary prediction. And so this essentially just boils down to 4 one-dimensional distributions to estimate. And it's basically just kind of a histogram or one-dimensional density estimation problem. And there's a whole bunch of methods in the statistical literature on how to do this, right? And there's lots of techniques for how you deal with data sparsity when you're doing this one-dimensional estimation. Once you have these probability distributions, there is a mathematically optimal deferral strategy that you can compute based on that. I'm happy to talk offline on the details of that, but for now, I'm going to just assume that we can do that. And so if we put these elements together, we get like a mathematically principled deferral strategy, and we can evaluate the deferral strategy in terms of what's called a ROC curve. So on the x-axis would be the false negative rate, and on the y-axis would be the true positive rate. And usually you would have a trade-off between the two. Like if, for example, you could predict negative all the time, then you would be perfect in terms of the false negative rate, or the true positive rate, and vice versa, right? So we're going to evaluate models based on ROC curves that look like this. And this is what we find. So this is a data set of patients from the UK that are part of a screening program where they have to come in every few years to get screened, whether they might be at risk for cancer. And the solid lines, the purple line as well as the purple line indicates the standalone diagnostic AI model performance. So that's already better than the green dot, which is a single clinician working by themselves, right? So the green dot is a single clinician. The purple curve is like the range of performances that you can get from a diagnostic AI model. And this dashed green curve represents what you can do by combining the diagnostic AI model with the clinician, right? So sometimes you end up using the purple curve and sometimes you use the green dot. And by combining the two, you can get this improvement in performance. Note that this is possible even though like this AI system is strictly better than the clinician working by themselves, right? So it doesn't have to be the case that the AI model has to be worse or better than the human to get improvements from this. The only thing we need is that there is some complementarity between the errors of the two systems, right? So if it's the case that the AI system makes different errors than the human, we can actually like improve performance in this way. The pink diamond up there is kind of the gold standard of care currently, which is multiple clinicians diagnosing the case and then arriving at a consensus. But even compared to that multiple consensus, if we defer to the AI, like if we use the AI system most of the time and then defer to the consensus of clinicians, sometimes we can get a further improvement in performance, right? This basically was like the main result we were able to achieve, that essentially we can outperform the golden standard of care in mammography while greatly reducing the number of clinician reads. You can think about how this would generalize to new sites. So we took the system trained on data from the UK and gave it a very small amount of data from the US and tried to adapt quickly to the US data. And we found that we're able to like generalize to the US data as well, even though in this case, it's kind of the situation is reversed, that the clinician performance is actually better than the AI performance. But even though the relative performance of the clinician and the AI is reversed, we're still able to get significant performance gains. So if we try to translate this into like what might be the potential clinical impact of deploying this, we can show that you can get up about a 25% reduction in the number of human reads required, which means that the system which was in place in the UK can move to the European standard of like screening patients every 2 years rather than 3 years with the same workforce. So you can see the same number of clinicians can see a larger number of patients or diagnose a larger number of cases in the same amount of time. We're able to like significantly reduce like dangerous errors. For example, 6,500 patients a year who would not have been flagged as risk for cancer who were incorrectly flagged previously will not be flagged. And in the reverse direction also we get some benefits. So that's kind of a summary of that project. And one thing that I left out in the previous section was that when we have this kind of integrated human AI system, I was assuming that when you defer to the human expert, they're going to behave as if they are diagnosing this case from scratch, right? That they don't have this extra context that there was an AI in the loop and the AI said that it's not able to make a prediction, right? So the question is like, when you have this context, is it going to impact the performance of the human expert? And so we did a project in collaboration with Liz, who was an intern with us a couple of years ago. So the goal was to study the following component, which is what we call the selective prediction message. So the idea is that if you decide to defer, what information do you communicate to the human expert you're deferring to, right? What information do you share with them about like what you try to do so that they're maximally aided in their own decision-making? Because it was a bit difficult to do this in the clinical context, we did this in this different context, which is wildlife conservation. So we're trying to detect the presence of animals given camera trap images. And this is useful for like tracking populations of, say, endangered species or like human animal conflict and these kinds of things. The goal here is that you have an AI system that tries to make a prediction, but if it decides that it's not reliable, then it's going to defer to a human decision maker. And the question that we are trying to answer is, what is communicated to the human decision maker when the AI is not reliable? So we experimented with 4 options here. The first one is that there is no message sent. So we're pretending as if the human needs to like make this decision from scratch. The second option is that the human is just told that the AI deferred, that it was unreliable and it refused to make a prediction. The third is that you just tell them what the AI would have predicted if it was forced to make a prediction. And the fourth is that you give them both pieces of information, that like what the AI would have predicted, but also whether it decided to defer, right? And so we experimented with all of these options. Ultimately, in terms of what the humans see, they would see the image. They would, of course, not see the circle. I'm just circling it here to show that there's actually a bird in there that's kind of hard to see. And then along with the image, they would see one of those 4 options at the top, right? So either no message or a message saying that the AI model is defers, or message saying that what it predicts, that no animal is present, or that both of these messages together. And then their task is to basically give a rating on a confidence scale that goes from 1 to 5. Okay, and before they started this labeling task, they were given some background information on like overall how well the AI is doing, some examples of where it gets things correct, some examples of where it gets things wrong, just so that they have some general context about the behavior of the AI system. And these are the results that we obtained in terms of the human performance under the 4 messaging conditions. And we found statistically significant results showing the humans just the defer message actually leads to a significant improvement in performance compared to the other conditions. So we're very curious about this result because it kind of seemed that like having both pieces of information might be better. But when we dug into the data a little bit more, we can analyze this data in terms of what we call the conformity, which is essentially this likelihood that the humans will just agree with whatever the AI said, right? And it turns out that if you segment the data by the human's own confidence in the prediction, when they have high confidence, they tend to have lower conformity. So if I'm very confident about what I'm saying, I will not be swayed very much by what an AI tells me, right? But if myself, I have lower confidence about my own prediction, then I'll be much more likely to be swayed by what the AI says. And if you connect this with this piece of information that we're only deferring on difficult cases, right? So all the easy cases, the AI is already able to handle. There's only some difficult cases where the AI needs to ask for help from a human. And in those cases, the humans themselves tend to have lower confidence. And so that's why it's kind of very dangerous to expose the human to the predictions of the AI system in these kind of difficult cases. How am I doing on time? Okay, cool. Maybe I'll just pause here to see if there's any questions on this part of the talk so far. Yes, please go ahead. Yeah.
Hi, I have 2 questions. The first is when you're getting the AI to give a defer message or a prediction, do you also show what the AI is predicting, as in which part of the image it is focusing on to give its prediction or not?
No, in this work, we didn't look at that, but there is work that shows that when the AI system gets the incorrect prediction, then the bounding boxes also will not be appropriate. So in fact, like in this case, when it said that it thought that there was no animal present, it's not going to give you a bounding box anyway. Right? And in fact, like most of the errors it makes out of that one. Okay.
The second question is, can this particular concept be transferred to other domains other than the medical application? For example, something like face recognition or maybe some other prediction tasks.
I think that in any domain where you have human expertise and that the nature of the human expertise is complementary to what AI systems are able to learn, I think this kind of system can make sense.
So I just need the model's prediction and weights, right? Or just
in fact, like the way we did this, we don't even need access to the model weights. We just need like the confidence scores from the AI.
Okay, thanks.
Hello. Sir.
So when you're referring to the human being, are you considering all the images to be equal cost in terms of labeling, or?
In this experiment so far, we were making that assumption, but I agree that it's not going to be a valid assumption always, and it's interesting to think about the impact of that cost.
I have a question in the graph, human accuracy graph, which you have shown.
Yes.
So basically, one is AI model is not,
The previous part of the talk?
No, this is this. Okay. Your AI model is not giving any message. And the second one is AI model is deferring the prediction. Now, deferring the prediction, how improves the human accuracy as compared to giving no message?
Yeah, so again, we haven't tested this rigorously, and we have some follow-up experiments planned. But the hypothesis is that the deferral message is a signal to the human that like this is a tricky case.
Okay.
And they should spend more time kind of on it as compared to other cases where the message is not.
Okay.
Ujjwal Gadaraju from TU Delft. Thanks, DJ, for that really interesting talk. It's not done. I'm sure you have lots to add to this. I have a few questions. The first one's about conformity, because that's the last thing you spoke about, and potentially what could explain these interesting results you found here, right?
Yeah.
And in some of our work in this same space, where we're also been looking into appropriate reliance, where you sort of want people to rely on the AI when it's probably more confident. You want them to rely on themselves when they're probably better off doing so, right? And that in itself is the difficult part, right? And over here, so I wonder where agency lies over here, because you've sort of said, hey, here's a deferral AI, right? That does this triaging for you. But how exactly does that relate to agency, and who has the final call?
Right. Yeah. So I think it's, of course, going to be context dependent. In our assumption was that we're working in a situation where like human labor is valuable. We want to minimize the amount of time we invoke human labor. And so we would like the AI to handle all the cases it's confidently able to handle, and only involve a human when necessary. But in the cases where it involves a human, the agency lies with the human. So the human is the ultimate decision maker when the deferral happens.
All right, I'll follow this up later on. But another question, or perhaps something you could reflect on, and this is something we found in some of our own recent work, where we were looking at human AI collaboration. One of the potential reasons why humans perhaps tend to inaccurately rely on AI is because of a bunch of cognitive biases, right? And one of which is called the Dunning-Kruger effect. I'm not sure if you're familiar with it, but it's this metacognitive bias where quite often individuals who are not very skilled at a particular task tend to overestimate their abilities. And that, adds up in shaping
I've seen
poor
this in
reliance.
the review process.
All right, well, yeah. Anyway, I'll just leave more space.
I meant like in general, like the peer review process, I've made this observation that like review.
Oh yeah, fair enough. Right. I do have a bunch of questions, but I'm wondering, I can see there's another hand there, and if it's time, I'll jump in again.
Hi, Dvij, Animesh here. So I was like more interested about that wildlife conservation thing that you spoke about. So there is a lot of work by Milind Tambe in this area.
So in fact, Liz was Milind's student.
Oh, okay, okay. So you are like doing something like with their systems, like you are trying to intervene their systems.
So I mean, the fact that we worked on, so our initial motivation was from the medical AI context. That we were trying to like think about these types of questions of like, what will happen if you have a deferral system that says to a clinician that the AI is not confident, right? What will be the impact of that on the clinician's decision-making ability? And in fact, there's some interesting work from some other researchers showing that in those kinds of contexts, like even though the clinicians themselves say that they don't rely on the AI, their performance goes down if they're exposed to incorrect predictions from an AI system. So this kind of cognitive bias exists even in the medical AI context, but because this was an internship project, it was a bit difficult to like get everything set up in the medical context. So we ended up doing it in this conservation.
I was just wondering, are these two problems not like inherently different? Because this is, as I understand, is a more high precision system, right? So it's a safety critical system that you are talking about. Whereas the other one, like one would desire like a high recall. Even if it's wrong, I would like to like, identify that there is some wild animal there so that we can stop poaching. So aren't they like a bit different in spirit?
I agree with that, but I think that the experimental observations are still valid, that exposing humans to potentially incorrect predictions from an AI system in cases where they're themselves not very confident about their own decision is dangerous, right? So I think this observation should hold even in the medical context. And in fact, there is some other research showing that that is actually the case.
Okay, thank you.
Hi, here.
Yes.
I think one of my observations has been with different models that are based on model scores. I mean, if the model scores themselves are not well calibrated, in the sense that it's very strongly predicting that an incorrect label. So I mean, how do you firstly sort of account for these in the deferral model?
Right. So there is a
second
let
part.
me just answer that question first. So there's a huge literature on like how to do better in terms of selective deferral than what we have done here. Our goal was to develop like a simple wrapper around like pre-trained AI systems, which doesn't require like retraining the AI and stuff, right? And there's literature that shows that like training an ensemble of models with like different random initializations and then averaging the predictions is a reasonable, if not optimal, baseline for uncertainty estimation in many tasks, right? So that's basically the uncertainty score that we ended up using. But of course, if you have better ways of doing uncertainty estimation, whatever those are, we can plug those into like the method that we have.
Right, right. Sure. I think a related approach, I mean, one is probably that, and then people have also tried to do consensus modeling, right? With employing maybe bunch of different models and taking their predictions, and maybe along with in some cases human predictions in a more cooperative sort of setting, which probably.
Yeah. So there, the consensus prediction setting differs a little bit because it ignores the cost of invoking a human. So our assumption here is that the human's time is extremely valuable, which is certainly the case for clinicians. And we want to make use of the human opinion only if necessary, right? So the deferral decision actually doesn't depend on the human label. We first make a deferral decision based on the model confidence score and only get access to the human label if the model decided that it wasn't able to make a reliable prediction.
Sure.
Can I jump in here? Because I think what you just said is super relevant to the question I was about to ask you, which was again, the CODOC system that you were talking about. And I was curious, this is more of a clarification to start off with. Was the system deployed in the UK?
No, this was like all like a retrospective analysis,
right?
Based on,
Makes sense. Also, because I think if
we
you
were
were
currently in the process of trying to do some of those prospective studies. Yeah.
Sure. Yeah. And I think one of the findings, from literature, again, people have been, trying to hammer this down and figure, because it's such a complex space, right? Yeah. So appreciate the work you've been doing here. I think when we do deploy such systems in the real world, one of the things that we've begun to observe also with, behavioral economists that we've been working with in the past is people don't really tend to behave in the way they tend to believe, right? So there's this big gap between trusting beliefs and trusting behavior. Yeah. And I wouldn't, so as much as you said, hey, there are potential implications where, you could probably slash down the number of clinicians who are spending time on doing things like this. I think eventually, if you were to deploy such a deferral model in the real world, you're saying, well, there is some direct impact of this decision that's being made without intervention of a trained expert, right? The clinician. And to what extent would that be something that's a digestible solution to the end user is questionable. So you've already said this contextual, but the medical AI is context itself is
there, like, in fact, like we did get some similar feedback even from other folks we discussed. And then I think it's useful to think about targeting situations where like the alternative would be like the user has zero access to medical care, right? So if the alternative is that they don't get any medical care, which is in fact like the case for, I didn't show, we have some results with TB detection as well. And for TB detection, it's certainly the case that there's many folks who are affected by it who don't have access to medical care. And so those cases it would certainly.
Thanks for your answers.
Okay. So I think given that, thanks everyone for the questions. It was great to engage in the interaction. I think I'm just going to quickly just outline the problem space that we tried to tackle in the next part of the project, and I'm happy to discuss details offline. So, so now we've described this kind of deferral system, and let's say that we have we get some access to a medical image and maybe some other information about a patient, and then we decide that the medical AI system is not able to make a confident prediction, right? Then we are asked that, we want to go to a radiologist and get their opinion. But now the question is, what if the radiologist is busy, but we have access to another type of clinician who may not be an expert in diagnosing medical images, but they still have some kind of medical knowledge, right? Is there something useful that we can do even in that context? And so the idea is that, rather than asking for the final diagnosis, can we ask for targeted questions which help us reduce our uncertainty about the final label? And so, for example, in many of the medical contexts, there would be clinical concepts, things like the presence of an infection or heart failure, which are relevant to the final diagnosis that you're making. And there may be experts who can give you feedback on these clinical concepts, even if they cannot give you the final diagnosis, right? So can you build systems which try to make a prediction, but if they are not able to do so, ask a clinician for help in terms of these specific clinical concepts, and then refine their prediction based on the feedback that they get on those clinical concepts, right? So again, like we experimented with this, like on a couple of tasks, both in terms of like recognizing bird species, where the concepts would be things like wing color or tail shape or belly pattern, those kinds of things, or like for chest X-ray, we can look at things like lung lesion and fracture, those kinds of things. So we built on this idea of concept bottleneck models, which try to first predict the concepts based on the inputs and then go from the concepts to the final label. And then we can reason about, like, if you had access to the ground truth value of some of these concepts, would it help you reduce your uncertainty about the final label? And we showed that, like, we can build such systems and get some improvements compared to like previous methods. So in summary, I would like to just conclude by saying that, human AI collaboration is going to be a key enabler of reliable and trustworthy AI. But building performative collaborative AI systems requires careful thought. We need to model and account for biases in human decision-making under AI inputs. And we need to also train AI systems to be proactive in acquiring and responding to new information at prediction time. So I think there's a lot of space for interesting research in this space. A few directions that I'm already thinking about, and I encourage all of you to think about as well, is this idea of two-sided uncertainty awareness, where there is uncertainty on the human side and there's uncertainty on the model side, and how do the two agents kind of communicate this uncertainty effectively? And another question which is important for like safety critical systems is explainability, right? So if I ask for a particular piece of information from a clinician, can I explain why I'm asking for that piece of information? And this, if we're able to do this correctly, it may have significant fair use and privacy implications as well. For example, if I'm collecting some health sensitive data about somebody, if I can give them a good justification for why I need to collect that data, that's a very useful capability to have. So with that, I'll just leave you with links. I guess you cannot click on the links here, but hopefully the slides would be shared. Thanks again. Some more questions.
So we have time for one more question, and then we will move to the next talk.
Hello.
Yeah.
So can you go back to the slides, older slide? Go back.
Which one?
Go back.
To the previous part of the talk?
This one.
Yeah.
So how are you detecting the set of questions when the radiologist is absent? Just the next slide, I think.
Right. So the assumption here is that like we have already curated a list of concepts which are relevant to the prediction task. And the questions will be related to like just asking for like the values of some of those concepts. So for example, in this case, it would be like, did the person have heart failure or did the person have infection? Those kinds of things.
So those things are already set up a questions based on a disease or something?
Yeah. So the questions are already curated, but the answers to the questions are not available to the model initially. And so the model tries to make a prediction without those answers. But then if it realizes that it's not able to make a confident prediction, then it can selectively ask for the values, the answers to some of those questions. Right. Again, the assumption here is that answering those questions requires an expert's time. So we don't want to do it unless it's useful.
And these questions might possibly follow up some other questions and possibly lead to some other questions also, right?
Exactly. So that's kind of the third level of interactivity that I was talking about, is kind of like the fully interactive system, where you can imagine that this is not a curated list. It's kind of an open-ended dialogue between the model and a human decision maker.
Okay. Thank you.
Yes, but even in that case, we may not want to do it potentially for privacy reasons unless we can justify like why we need access to that information, right? Or in some cases, it may involve like subjecting the patient to some other additional medical test or something. And again, we don't want to do it unless it's necessary.
Questions can be answered by the patient with all this constant, then the cost immediately can go down.
Yeah, for sure. So if there is information we would have access to anyway, no matter what, then we should certainly make use of that information, right? So, but then it's just saying that we have access to additional features initially, even before like the initial prediction. But the question here is that if there's additional things beyond that, that have some cost of acquisition, can we be selective about acquiring those?
All right, thanks a lot. So here is a small token of appreciation from the organizing team. Thank you.
Thank you to the organizers.
So next talk is by Professor Dweepobotee Brahma. Dweepobotee is an assistant professor at the Center for Mathematical and Computational Economics in the School of AI and Data Science at IIT Jodhpur. Her research interests lie in the intersection of applied econometrics and health economics. Title of her talk is Econometrics and Machine Learning, Two Old Friends.
Am I audible? Yeah. Good morning, everyone. So this talk is going to be of a quite a different flavor. I'm an economist by training, and I'll be talking about how machine learning is employed by economists and the wider world of social scientists. And this will be a very general talk. I'll talk about studies that have employed machine learning and the pathways in which we have employed machine learning. Okay. So I'm talking about machine learning and econometrics. I'll talk a bit about econometrics and how it's what it is and how it's used not just by economists, but other social scientists. So to know what it does, we have to think back about what economics as a discipline studies. And I like to start my talk with this because there's a lot of notions about what this discipline actually does. But the crux of the matter is that this discipline is actually quite broad and quite narrow at the same time. It's a bit paradoxical. So what is it? Economics is the study of choices that we make under scarcity. Okay. All econ questions arise because of this fundamental idea that we have unlimited wants, but limited needs, limited resources. And that leads to scarcity, and we need to make choices. But the interesting part is scarcity can be scarcity in absolutely anything. Okay? It usually starts with scarcity of money. We have a budget constraint, right? We have a limited amount of income that we need to allocate amongst, the things we want to buy. But actually, the discipline is far broader. We look at scarcity of personnel. So that's labor economics. We study how to allocate individuals with skill sets in different professions and different roles. We study physical infrastructure. We study time and attention. So this is all this new hot field of behavioral economics, where we study how individuals make choices when they have scarcity of attention. And from econ theory, it helps us identify deterministic relations about the world that we study. Okay, so it tells us about the direction of change in one variable in relation to the other variable. But the thing is, data does not evolve that way. Okay, there is a high component of uncertainty in data. And so econometrics, which is the study of measuring economic concepts, has to study variables that are stochastic in nature. So we go from this deterministic world to a world where we have to make probabilistic statements. And so we start using expected outcomes. So I want to draw your attention to how we take theory from economics and social science to models. Okay, so we start by taking a statement from theory and we use it. We test the statement using data. So it goes from theory to data to statistical models. Okay, and so the first time this term was coined, econometrics, was by the first, the co-winner of the first Nobel Prize in economics by Ragnar Frisch. And he talks about this, setup where he talks about econometrics being a mixture of economic theory. It's not just quantitative economics. It's not just mathematical economics. It is a combination of all of these. Okay. Now, this quote, it's verbose. It basically talks about how econometrics is this intersection area of theory, mathematical modeling, statistical modeling, how data evolves, and takes a combination of all of these, right? Now, this should sound familiar to at least some of the students, right? Because this is very similar to how we define data science, right? Data science is defined as the intersection of, you don't just take theory, you don't just take statistics, you take the combination of all of those. So it's domain knowledge driven modeling. But where this gets interesting is the pathways in which we incorporate domain knowledge. Okay, so there is emphasis on incorporating domain knowledge from economic theory to build models, but developing statistical models for answering economic or even wider social science questions puts it on a very specific trajectory. Okay, and I'm going to talk about those trajectories in my talk. So what is the focus of this discipline? Okay, it fundamentally focuses on questions related to what we call the marginal effect. Okay, so because we have to make choices under scarcity, right, we have to know the measurable consequences of those choices. So say a government is trying to decide, how much money to allocate to a particular policy. Okay, so some of you might be aware of, we have this universal immunization program in India. Okay, and every year during the budget, money is allocated into this program. Now, a state government or the central government might be interested in knowing how many extra children can be vaccinated if you just allocate an additional 1 lakh. So the questions we ask are very specific. We ask the question of how much. We want to measure the impact of a particular decision. And that puts us on another path where we are focused on talking about causality. So is it my action that causes a particular impact, or is it something else in the environment? Okay. And the fact that, as a social scientist and economists particularly are obsessed with looking at these two channels, this determines how we use AI and machine learning. Okay. So this is an audience of, mostly computer scientists. So I won't talk about the machine learning part, but I'll tell you about where we fundamentally diverge in this path. So, the starting point of almost all empirical modeling has been the simple linear regression model. And so it's like this big bang of statistical modeling. And when I teach students who are mostly from a machine learning background, they're all familiar with this. If you come from a statistics background, you're familiar with this. You come from a social science background, you're familiar with this. But the difference lies in what path you're on. If you're from a machine learning background, you study this and you're immediately on the path on focusing on this y hat. Okay, so you start with how simple linear regression is used for prediction. We know it doesn't do a great job, and you learn about all the other algorithms and models that focus on prediction. But if you go back in time and you go back to when you first learned it, social science, economics is all about the beta hat. Okay, so we are all about this parameter right here. It tells us, it gives us the answers to the two important questions that I said, how much and why, right? All about marginal effect and causality. So given that, at the very beginning, at the starting point of learning empirical modeling, we tend to diverge, we tend to go on two different paths. How does social science actually incorporate machine learning? Okay, so I'll talk about three common streams of research, and talk about different studies that have incorporated these three streams of research. The first is where we use machine learning to get non-traditional data. So in empirical social sciences, we rely a lot, and this has been the norm, the tradition in the disciplines for a long time. We rely a lot on surveys, census. These are traditional sources of data. And they're actually very good because they have this property that we can compare changes over time, because the sampling strategy, the way we collect data has stayed almost the same over time. But now with the advent of these machine learning tools, we can get non-traditional data. And I'll talk about what that is. So we can get data that's, we would call it usually big data, large unstructured data, night lights, satellite imagery, all of this to help us, add to our analysis of what we can get from traditional sources of data. And so that's one stream. And I'll talk about a few studies that have effectively, addressed this. The second stream are pure prediction problems, And this is something that you see most around. So if you see applications of AI in social science, this whole field of AI for social goods, you'll see a lot of prediction problems. These are where we predict outcomes in health, labor, economics, education, and so on. And the third, that's currently, the hot area in social science is combining inference with prediction. And this is where there's been a lot of contribution recently in economists contributing to this literature, where we are using our notion of how we look at causality and combining it with machine learning. So let's look at these streams one by one. So the first, is about how to use big data in machine learning. So I'll talk about a few problems that we face in social science research and how we have incorporated ML to solve these problems. So the first one is that we need to very often estimate concepts, measurements of wealth, GDP, economic activity at various levels. And so when we use traditional data, they are usually representative up to a certain level, and which is usually the district level. So we are able to get, using traditional data, we are able to get estimates of GDP at the state or district level. But in a country like India, this is true for most developing countries, there is a lot of heterogeneity even within a place like a district, because a district is quite big. And so traditional sources of data take a long time to collect. We usually get it at very long intervals. So if you know a bit about our census, it's conducted every 10 years. So that's a long time. An economy changes a lot during those 10 years. So we are able to use satellite imagery, to cover, it takes data on luminosity and from this artificial lights, night lights, and you can get a measure of economic activity at a much more spatially granular level, So you can get measures of economic activity even at the block level. So there's this fantastic paper, I'll show you an image of that, which has used night lights to generate local estimates of economic activity and even poverty at a census block level. Very recently, during the COVID lockdown, it happened, towards the end of a decadal period. So we don't have, using census data for 2019 and 2020 wouldn't be too great, because we know the economy has changed quite a bit since our last census. So very recently, a study looked at the effect of COVID lockdown on economic activity. And you can see that using night lights, how much change has happened during this COVID period. So to give you a glimpse of what it can tell us, this is a seminal work from one of the earliest works that uses satellite imagery to get at a measure of economic activity. So the left is what India looks like in 1994, what India looks like in 2010. And so you can see the stark difference in how much more economic activity has happened during this decade. Okay, so you can use this the luminosity data to actually capture changes even between censuses. Okay, some more uses of machine learning. So there has been quite a few talks until now about using natural language processing. So one of the problems that we face in social science is that measures of policy, sentiments and tones about policy do not have a very good, well-structured, quantitative data. Okay, and so you can mine government bulletins, memos, press releases to construct text-based indices of cross-country comparison of industrial policy. And so this work right here, it's very new. It has just created a global database of economic policies. Okay, fantastic work that has mined government memos and press releases and so on. Okay, a slightly a work from last year. They use data set from 80 million cases in the Indian judicial system. So if some of you may not know about this fantastic data set on India Kanun, it has uploaded the case documents of almost all cases tried in the local courts of India from 2018 to 2019. And so this particular study, it's a gold mine of, for researchers. This particular study tried to look at in-group biases. So something that social scientists care a lot about is, does the gender or religion of the judge give you a favorable outcome if it matches with, the gender or religion of, say, the defendant? Okay, and to be honest, they don't find a lot of they don't find any effect of in-group bias, which is something that surprised a lot of people when this paper came out. Okay, so again, another way we use non-traditional sources of data. Okay, so talking a little bit about the second channel. Okay, and this is where it gets really interesting. I talked about looking at marginal effects through the model parameters. And what that tells us is we get to know the average treatment effect of an intervention. So we know on average how much a particular intervention affects a population. Okay, and that's great. That gives us a measure of how much money to allocate, how much attention to give to a particular scheme, and so on. How do we use ML? ML helps us identify who to target. Okay, so we know how much if we want to look at the effect on average of a population, but suppose we want to go more granular. Okay, and so we use machine learning to tell us who to target interventions to, and it answers our more fundamental question about what we do in this discipline, which is better allocation of resources under scarcity. It can also answer the where, who and the where. So we'll look at a few studies that have done exactly that. Okay, so one problem that public sector grapples with across most countries is this allocation problem of monitoring. Where do you send inspectors? Where do you send traffic police, right? And there's always a limited number of trained inspectors that can do good monitoring and evaluation of any scheme. And so something that the city of New York grappled with for a while was how to allocate fire inspectors. Okay, and we find that if you use a machine learning algorithm to look at the predicted probability of a fire event occurring in a building, we're able to get at least a 30 to 40% improvement in this structure. we are able to save, buildings from a fire event up to a 30 to 50% of the times. This is also similar to another work where Ed Gleiser from University of Chicago looks at allocating health inspectors to restaurants in Boston. So something that in Boston is very strict about this. They have, these impromptu inspections of restaurants to make sure that they're up to code. And again, it's important to send trained inspectors to look at restaurants, but we only have a limited number of these inspectors. And so using an ML system, we're able to better allocate these inspectors. Some more work in this area. So I'll talk about a few, what kind of questions these studies answer. The first one, Lenz, he tries to predict food security status in Malawi. And this is particularly interesting because this paper looks at incorporating, a wide range of data. So it covers both the streams that I talked about. So they look at granular level market data from, local markets in the region, remote sensing data of rainfall, demographic characteristics of the individuals living in the country. And what they're able to predict is which local region is going to, run out of food during the famine. And so this answers the where question, which means that where should a government target aid to? Which local level, which local block? The second paper, it also tries to predict similar to what I talked about, the satellite imagery data, but this time they're predicting poverty. So if a government wants to open up, public distribution stores, like, India, we have something like the ration stores. If your goal is to open up these public distribution system stores, using satellite imagery data, you can get granular level estimates of poverty, which will tell you where these stores need to be targeted. The third is some of my work in this area, where I use an ML system to get early warning signs for adverse health outcome, which is neonatal and infant mortality. And so these early warning systems can be used by rural health workers, and they can triage individuals who are at risk for suffering from neonatal infant mortality and refer them to district level hospitals. The last one, and this is a really interesting case. In social sciences, we rely a lot on these large scale household survey data. And one of the interesting, topics currently that is being studied by a lot of people is how to measure the amount of agency individuals have within the household, especially women. Are they able to make decisions related to their health, financial decisions related to their children's health, and so on? And the current structure is that these household level surveys, they give these women a large set of questions to answer about, who makes a decision in the household. Now, what happens in these surveys is that at the end of the survey, people suffer from cognitive load. They don't want to answer these questions, and they end up answering them, in a very casual fashion. So we are not able to get a very accurate picture of what the level of agency really is. And so the last study that I'm talking about here, they look at this, a set of 50, 60 odd questions that these respondents are asked, and distill down that information to 2 or 3 questions, which actually capture all the information that you need in order to find this agency score. So if your data asks those 3 or 4 questions, you will be able to get all the information you need to build an agency score. Okay. So a few, different ways in which prediction problems can be used in social sciences. Okay, now turning to the third channel, which is causality. Now, this has been a very big part of economics, econometrics, and social science discipline. Okay, and it has been a central theme, and we look at it from a very particular framework, which is the, if some of you are familiar with this, this is the Roy-Rubin model of the potential outcomes framework. And it's popularly called this what if scenario, right? So we try to look at what happens in the world without this particular intervention and a world that does have this intervention. And so, despite recent advances in field experiments, so if you're a bit, plugged into the social science field, there's been a bit of a revolution recently where we've taken these experimental setup that has until now been stuck in the labs to the fields. Okay, and so 2019, the Nobel Prize for Economics went to the lab in the field type of studies. Okay, now there's a lot of talk about this. There has been quite a few experiments, some very good advances made in policymaking with the results derived from these experiments. Despite all of this, most of the data that we work with in social science is observational in nature. Okay. Experiments, especially in fields, are very long. They take a very long time to run, and they're very expensive. So we mostly rely on administrative data and observational data. That makes questions of causality very difficult to answer, right? And so additionally, we work a lot with what is non-IID data, which is not, not data that can be swapped, right, with each other, instances that you can't swap with each other. There is an inherent structure within the data. Again, not something that lends very easily to machine learning algorithms. So some of this, these are just the names of some of the techniques that I want to touch upon briefly to talk about the fact that this discipline has seen this credibility revolution recently. So we have the first set of studies which use this randomized control trials or lab in the field experiments. It was the first Nobel Prize in the 2019. And the second is this other field of natural experiments or quasi experiments, which when I go out of this social science bubble that I sometimes stay in, I don't see a lot of knowledge about this. So this entire field is about how do you infer causality when you cannot do experiments, okay? And this is where we see a lot of involvement of AI and ML coming into the picture. And this comes from the Roy-Rubin model of this what-if framework of potential outcomes model. And everything that I've labeled after that, these are all different tools that follow this natural experiment setup, okay? And so we have this, difference in difference, event study techniques, regression discontinuity. These are all ways of using this Roy-Rubin framework to get at causality. So let's look at a few ways in which economists have contributed to this. Now, for those of you who are not familiar in the audience about this causal framework, we always go back to this idea of what is the fundamental problem of causal inference in this framework, okay? Which is that, for any individual, it could be a person, a family, a firm, whatever, you only get to observe one of the two potential outcomes. So when an individual is subjected to an intervention, there's two possibilities. One is what his or her outcome looks like when he has been subjected to an intervention, and one is what it looks like if he has not been subjected to an intervention. However, in the world that we live in, especially in observational data, you get to see only one of these, okay? So which brings us to the idea of how do we infer causal effect? In order to really look at causal effect, we need to have observed both realities. One where the event happened and an alternate reality where an event didn't happen. Okay, so it's kind of like, if you're familiar with the Marvel universe, there's this other universe where this reality didn't happen. Okay. Now, of course, in data, we can't observe these two realities. So all that we do through this natural experiment, quasi-experiment framework is to find a way to reconstruct that alternate reality. What would have happened to an individual if he or she wasn't subject to an intervention that he or she is subject to right now. And so it looks at this causal inference framework as a problem of missing data. It's like we don't have data on that counterfactual. And so all of these methods, okay, they boil down to reconstructing or uncovering this missing data. Or in other words, we are trying to predict the counterfactual. So if you've been following my train of thought in this, through these slides, you know where we are encountering the use of machine learning, right? So you can now use, machine learning to get good predictions of this counterfactual. Okay. So this particular stream of research is exciting in the social science field. And it's also because this is where economists are contributing to the world of machine learning. So I'll talk about three kinds of ways in which we are looking at it. The first is something that is very important in observational data, is where we have to incorporate different covariates, different confounders in our study to make sure our study doesn't suffer from bias. So when we fail to control for good confounders, we can have biased estimates. It can even be true in observational studies, okay? You need to control for confounders to make sure that your randomization has been done correctly, okay? Now, this particular tool, something that has been created, it's kind of taken the social science world by storm, is about how you can use selection algorithms, and you can use it twice, hence the name double lasso, in a very principled manner to account for avoid not incorporating correct confounders. And it helps you conduct inference to avoid inflated type 1 errors. So not falling into the trap of making false discoveries. So I won't go into the steps, but talking a little bit about how this is particularly useful. So let me talk about a study that has actually used this effectively. Okay, so in the world of using lab in the field experiments, and some of you are familiar with using behavioral studies like nudges to get people to do things. There was a large-scale experiment run in India about getting people to take child vaccinations, okay, getting their children to get vaccinated. Now, child immunization, it's one of the most effective low-cost ways to reduce mortality and morbidity in the developing world. But we find that over time, it's kind of hit a plateau. Okay, and take-up has been the last mile coverage of child vaccinations has been, kind of stagnant. Okay, so it's hard to reach those last few people. And so this study ran a large field experiment using many different kinds of nudges. So nudges are these small incentives that you can give to participants to push them to get their children vaccinated. And so you have nudges like cash rewards, you have nudges like in-kind rewards. So in rural areas, you can give nudges, you can give like rice and dal, SMS reminders. So a lot of work has been done by sending SMS reminders to individuals to get their children vaccinated, get their children enrolled. Also the use of networks in society. So if you'll find that within a rural village, there's often these influential individuals that everyone listens to. They could be gram panchayats, they could be just some elder person that everyone likes to listen to. And so planting an information in that person, like telling that individual a particular information, spreads very effectively through the rural network. Now the problem that we often face is all of these nudges have been shown to work in some contexts, not so much in other contexts. And more importantly, they could work with each other or they could cancel out each other. Okay, so it's not like any one nudge will work, but it's like, they could work together, go hand in hand. And so how do you know how to make this work? Okay, So you could also have different dosage variants of this. So it could be like if you give a small amount of monetary incentive, it doesn't work, but a large amount of monetary incentive does work. Okay, so these are questions that, as policymakers often grapple with. So what the issue boils down to is that there are so many possible combinations of these nudges that can work, but we can't try out all of them. We can't implement all of them. Okay, so we need to implement, only a handful of them. So this particular study implemented these 10 different nudges. And the question that, was posed to policymakers was that we needed to know which of these nudges is the most effective. So this is where we are coming to the how much question, meaning how many extra children get vaccinated if you do this nudge, and which of these is the most cost effective in terms of like per unit cost of doing this, implementing this nudge. Okay, so from these 10 possible nudges, we get 75 different combinations. Okay, and we use this new selection-based algorithm, causality algorithm, that is supposed to give us ultimately the answer to which of these has the largest impact. And what the study finds is that it's actually these SMS reminders to individuals along with information hubs. So these are individuals who are influential in that social network that turns out to be the most effective and cost effective. Okay. So I have 5 more minutes. So I'll talk about a few more ways in which we've incorporated this world of causality. The other is something that policymakers often grapple with, is how to understand how different subpopulations in a particular area respond to a particular treatment. So you could have standard econometric models. They'll give you the average effect. You can expand it. You can expand your model by looking at different interactions, but there's always this ad hoc problem, right? So you as a researcher, you decide what kind of interactions to look at. But what if we take the world of machine learning, okay, where we have these data-driven methods look at interactions, okay? So many of you are familiar with the random forest algorithm. And so the recent innovation in this field has been to take this random forest algorithm, tweak it, okay, to tweak it in a way that it no longer is used to predict a particular average effect in the leaf, but we'll tweak it to look at conditional average treatment effect, which means that what is the effect of that intervention, and identify which subgroups can be used to, which subgroups respond the most to treatment. Okay, so we use a data-driven method to look at what combinations of demographic characteristics gives you individuals that respond the most to a particular treatment. This has been deployed in a study in downtown Chicago, where the government ran a summer jobs program for disadvantaged youth. And out of those individuals, they are able to apply this particular algorithm. It's called the causal forest. We take the random forest, we give it a causal twist, we call it the causal forest. And it identifies 2 specific subgroups of population using demographic characteristics on whom this particular intervention was most effective. Okay, last 2 more, and these are, I promised to talk about areas where, there's still a lot of scope and very, very new areas where machine learning is being used in tandem with econometrics. Now, one potential goal is often to look at, which policy out of a range of possible designs has the greatest impact on a particular outcome. And traditionally, we've done this using, say, observational studies or lab in the field experiments or randomized control trials. Now, I talked about the fact that these are painstaking. Okay, they take very long to implement. And the thing is, you have to wait until the end of the experiment to know the result. Okay, but we can give a twist to this. How is that? So there's a very recent work that uses adaptive sampling, an adaptive experiment design. You combine this with, stuff from the machine learning world, which is the reinforcement learning techniques, and you get a new explorative sampling design. So how has this been used? And this is particularly, interesting. So there's this NGO called Precision Agriculture for Development. They provide information to farmers in, information that can help them, have a higher yield, help them optimize their planting and selling of crops. And what this NGO was interested in doing was they wanted to reach as many farmers, and they wanted to quickly learn which one of their possible treatments works. They were not interested in waiting until the end. That would take too long. They wanted to learn very quickly about, how to provide information with these farmers. The thing is, farmers, they're busy. They figure out very early how to screen calls. So if you call them at a time when they're really busy, they're going to screen your call. So the NGO wants to know at what time during the day should you call the farmer so that that person listens to the end of the call, okay, listens to all the information that you have to provide. And so you can use this, dynamic sampling, dynamic treatment to figure out, and they found out that calling them at 10 a.m. in the morning before they start their day and following up with an SMS afterwards turned out to be the most successful treatment. And when they figure this out early on, they're able to implement this on many more farmers and get a higher return for the strategy that they implement. Okay. Last one, and this is something that's very new and particularly close to my heart. One of the topics that we study in social science, not just in economics, even political economy, sociology, is this idea of equality of opportunity. Okay? And it's an idea that comes from distributive justice, which means that the amount of unequal opportunities that individuals face in society. So what is this fundamental idea? That in a world with equal opportunities, okay, so if everything was equal, you had access to all resources, all individuals would have the same chance of, climbing up the social ladder, climbing up the economic ladder. So everybody would have the same chance of getting a same outcome. But we know that that's not the case. Okay, we know that the circumstances of our birth have a very high impact on where we end up eventually. And that's the part of this, inequality, that's part of this inequality opportunity that we call the unfair advantage, that how much the circumstances of your birth affect where you eventually end up in life. And so I'll wrap up quickly, but the idea comes from the fact that all factors that determine where you end up at the end of your life can be split into two parts. One is what we call circumstances, and the other is effort. Effort is what the amount of work that individuals have put in the life, and the inequality in outcome that stems from effort is not particularly unfair. But inequality in your final outcome that comes from circumstances of your birth is the part that's unfair. So we want to know how much these, birth outcomes affect where you end up in life. And so we can use a kind of tree, a random forest algorithm called conditional inference tree, to identify categories of individuals whose, circumstances at the time of life determine where they'll eventually end up. So I'll show you two particular cases. This is from a study that's looked at what this opportunity tree looks like in case of a country like Sweden. So you see that, if you look at where individuals end up, it's just their, one factor, the birth area, which shows whether individuals were native born or born within the EU, that determines, where they'll end up. So not that big a deal. Contrast this with a country like Germany. You see a much more complicated tree. And you see that there's so many factors like father's occupation, education, whether the mother supervised you while growing up, which determines where individuals end up in life. So you can, look at how many factors are a part of this inequality of opportunity are a part of your circumstances which determine where you'll end up. Okay. So I'll leave you with these possible ideas of how social scientists, especially economists, are using, and leave you with the thought that machine learning, artificial intelligence, and economics is more than just the sum of its parts. We've taken some ideas from the machine learning world into our world. We've taken ideas from econometrics to build new machine learning algorithms. And so hopefully this is just the start of a very fruitful collaboration between these two disciplines. Yeah. Thank you.
Thank you, Dr. Brahma, for this wonderful talk. So any questions? We have time for a few questions.
Thanks for the great talk. So I had a couple of questions. One was in the early part of your talk where you mentioned using satellite imagery for, so I was wondering, like, what's the concrete economic question are we trying to answer there? And how sensitive is it to the accuracy of the ML approach?
Sorry, the last part,
how sensitive is the answer to that question to like the accuracy of the ML approach that we use, and how reliable does the ML?
So the first question, the answer to your first question is, what are we trying to do? We are trying to get granular estimates of some economic concept. It could be GDP, it could be wealth, it could be poverty, but we want to generate the estimate at a very spatially granular level. So not district level or state level. We already have estimates of that from traditional data.
Right.
We want it at something like a census block level. Okay?
No, I understood that goal, but like I wasn't clear about like how you can do that just based on, for example, like lighting.
Sorry, how?
How you can do that just based on like estimating like satellite images,
So
like lighting.
satellite imagery gives you, so there's a you get a pixel, a data with every pixel has luminosity in it, right? Now the idea is, as the economy grows, especially now in a modern economy, how luminous a particular area is a function of how many businesses, houses, etc. are in that area. Okay, so the night light data is what gives you that luminosity. The more concentrated, aggregated an area is, there's prior research which tells you that the richer that area is. Okay. And so the more bright area you get a particular pixel, it means, the richer it is. Now, of course, there is an algorithm in the background which converts a measure of that luminosity into a measure of wealth.
I see.
Yeah.
So I can see how a qualitative comparison can be made. I'm kind of finding it difficult to say that you can actually give an estimate for the actual GDP.
Yeah.
Based on this, that seemed a bit far-fetched.
It's not the best.
It's
the second best.
Okay.
Yeah. It's not, so to answer your question, what do we use it for? It gives us a broad idea of how a region has transformed over time. So with the same satellite that's taken pictures, everything else staying constant, you can see how a particular area has grown over time. Yeah, but we wouldn't use something like this to target aid because it can be quite difficult.
My second question is around like identifiability issues in like, estimating these causal effects and those kinds of things, especially if you have like small amounts of data. Like, do you worry a lot about like, essentially like variance of statistical estimates and like trying to figure out?
We worry a lot about that. So there's this whole literature on small sample bias, getting accurate standard errors, bootstrapping standard errors, like a whole different thing in econometrics about how to make sure variance estimates are robust in a small sample.
Because doing that with like deep learning is all that much harder, right? So
so I don't go into all of that in my talk, but it's a whole subfield in econometrics over the last 10-20 years.
Thanks, great talk.
So there is one question.
Hello. Am I audible?
Yeah.
Yes. So thanks for the talk. My question is, like in economy, we know that the large part of the government revenue, it comes from the direct and indirect taxes that we pay either through the individuals or the organizations. So we also know that the government is missing out on its major part of the revenue due to the tax evasion or due to the non-compliance of the taxes by the individuals. So my question is, how feasible or practical can be machine learning in identifying the potential economic offenders, either through the raw data like the individual income patterns or the policies or anything? Like, for example, if the per capita income, it increases, but your tax footprint is same. It does indicates that there is more tax evasion.
The short answer to your question is not very well. Okay, because ultimately all algorithms depend on data. Okay, and so the thing about tax evasion is if you want to evade taxes, you don't want to leave a paper trail, right? If you don't leave a paper trail, then data is hard to get. Okay, so can we identify individuals who have evaded taxes using machine learning? I don't know of any successful study that has done that.
And they also become big buyers.
Yes, yes. Okay, so the short answer to your question is, sorry, algorithms can't help us fix that issue.
Thank you.
Okay, so we have time for just one more question.
Okay.
Yeah. So, no, I was waiting. Okay, you can take it. Okay. Thanks for the wonderful talk, Dweepobotee. So I have like a few disconnected questions. The first one is like around what Dvij asked. So I was thinking like, why not use interactive maps like the amount of traffic, the number of restaurants open, like those kind of data. So are they like even worse than the second best?
No, 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 they are used. So I have not included that in the interest of time. But so night lights was the first of non-traditional data to be used. Okay. Now there are studies that incorporate, restaurants, traffic flows, so there's some more work that looks at Google images from Google Maps and looks at, what the houses look like in a particular area to determine median income in that zip code in the US. So the answer to your question is we are increasingly using more types of non-traditional data, but each have their own sets of biases, and so we have to make sure we take the right kind.
So the second question was around this machine learning prediction vis-a-vis the randomized control trials. Like there should be a trade-off between these two, right? So like when do you prefer to do randomized control trials and when do you prefer to do machine learning to get the prediction? So are there some studies around that?
So the answer is it depends on the question. Okay, so when do we prefer to use randomized control trial? When we want to know the exact measure of an impact of one intervention. When do we use both? We usually use, so in the context that I was talking about, we use machine learning after running the intervention. So when we want to look at, which possible intervention had the most effect. Okay, so we take all combinations. So we try to select which is the best predictor out of that.
Okay, and the last one. So the last one was like related to the end of the slides where you are talking about disparate treatment, like in terms of equal opportunity.
Yes.
So it has been seen that it's typically around some sensitive attribute. So were you assuming the region of birth to be a sensitive attribute in this particular example?
So sensitive, do you mean in the context of privacy? Like sensitive how?
It's like sensitive in the sense like something which you would not want to have a public disclosure of, like the race, ethnicity, and things like that.
Yeah. So race is not used. So the study that I was referring to used survey data. Okay. Race, place of birth. These are all, so we use data that individuals have reported. Okay. And in this particular context, it's not as sensitive because it's anonymized data. So we don't know who is the individual who's reporting race or who is reporting their area of birth. But so I'll just finish how we use it. So the idea here is what we are trying to see is which one of these circumstances over which the individual has no control, right? We don't have control over our race or where we are born. Which of these contributes to inequality of income as an adult?
Yeah, so I was just wondering, it might well be the fact that the geolocation is connected to the race.
Yes. Yes, absolutely. And so, so perhaps it's not evident in this particular tree, but in looking at other countries, the conditional inference tree actually picks up that interaction. Yeah.
Thank you. Thanks a lot.
Yeah, thank you for the very interesting talk. So I think a few years back, we were creating policies for AI. Now the AI is in the stage where it will create economic policies. So yeah, so on behalf of organizers, let me just present this moment to the speech.
Thank you. Thank you.
Thank you very much. Yeah. So we have three main announcements. So first announcement is participants who have not yet registered, please get yourself registered. So the registration desks are set up just behind this auditorium. The second announcement is for students who are shortlisted for the travel grant. So you have to submit all the documents that we have already conveyed to you at the registration desk, and you have to sign some of the other documents as well. So this process is now started and will continue this process till today 6:30, and then we will start the verification process. The third announcement is related to the lunch and the poster. So the entire lunch arrangement is done on the right side of this auditorium, and on the right side of the lunch venue, the posters are arranged. So there is a nice kite kind of an open space. You will see a lot of kites on the roof, and this is where the posters are arranged. So Professor Pawan Goyal will explain will kind of give us the details of the poster presentation now. Thank you.
Yeah. Thanks, ma'am. Very quickly. So we have around 1.5 hours for the poster session and lunch, and there are around 36 posters. So all the participants are requested to visit the posters because that's where the students will be there and they'll be interacting about the work. Mainly for the students who have the posters, can they just raise their hand? Who have the posters? Okay, so we will have top 3 posters evaluated during the session itself. And we have 4 esteemed judges who will be helping us coming to that decision. So if the judges are here, I'll just request them to raise their hands so that the participants know. So we have Professor Mohit Iyer, who has already given a talk. He's one of the judge. Professor Rishabh Iyer, he would be around. Dr. Parth Gupta from Amazon Research, yes, Dr. Parth Gupta is here. And Professor Shanmuga Rajan from IIT Gandhinagar, he's also around. So these are the 4 judges who will evaluate your posters. So this is a working lunch, so you can take your lunch, the participants can take their lunch and be at their posters. Try to be there by 1:15 if you have a poster so that the evaluation process can go on. And others, please go and interact with the students. I think this is all I wanted to say, and happy lunch. Thank you.